right, welcome to lecture 7.3. I see that, Jeremy. Lecture 7.3 covering the unit circle here. This is going to be, this piece of info, or this amount of information that you're getting tonight is going to be extremely important for the rest of the semester. So please make sure that you are taking good notes along with me and wrapping your brain around this stuff. And by all means, for the folks that are in the room with me tonight, feel free to ask any questions. Okay, so the first thing that we encounter in this particular section is just the idea of finding the trig functions using the unit circle. So you can see I have actually 3 unit circles drawn here, well, at least pieces of unit circles, that one in the center. And the way that I know that this is the unit circle that we're looking at is because we have a radius of 1. So we've got radius 1 in all 3 of these pictures here. So what we find out here right at the beginning is that for any angle t, so the angle t is always the angle from the positive x-axis to the terminal ray of the angle. And they're calling it angle theta on that picture there, but it's the same thing, t, theta. It's just, that's just a way of naming the angle. We can label the intersection of the terminal side and the unit circle by its coordinates, x, y. So where that terminal side and unit circle meet is a point. So it's a point on the circle. And the coordinates x and y will be the outputs of the trigonometric functions cosine t and sine t respectively. So what we are given here is that due to the relationship of sine being the opposite over the hypotenuse. Remember, we have SOHCAHTOA that we learned in a previous lesson. That helps us remember our 3 basic trig functions there. Sine is opposite over hypotenuse. Well, in all 3 of these pictures, our opposite side is that y value. It's the length of that side of the triangle, which is going to take us up vertically to that y value. So sine is equal to opposite over hypotenuse. So what we get here is that the sine of that angle t or angle theta is your y value. And our cosine, let me get a different color here. Remember, cosine of theta is equal to the adjacent over the hypotenuse. Well, our x side, or however far horizontally we move out before we go up to that point on the unit circle, is our adjacent over our hypotenuse. It ends up being just the x value. So you can actually call the coordinates of any point on the unit circle cosine theta, sine theta, instead of x and y. So green check if that all makes sense as to how we can actually rename the coordinates of a point on the unit circle cosine theta, sine theta. Okay, I've got 3 green checks. Matt, are you with us, man? Okay, I'll take a smiley face. Okay, so then below, that's just an explanation of the coordinates there, which we just talked through. So that's just part of the notes section of your textbook that I included on these notes. Okay, so defining sine and cosine functions from the unit circle. So like all functions, the sine function has an input and an output. You're going to input the angle that you're taking the sine of, and your output will be that function's value. Its input is the measure of the angle. Its output is the y coordinate. Remember, we're talking about sine. The coordinate of the corresponding point on the unit circle. The cosine function of angle t equals the x value of the endpoint on the unit circle of an arc of length t. Remember, t is that distance from the initial side to the terminal side, and it is equal to that length. Okay, so because it's understood that sine and cosine are functions, we do not always need to write them with those parentheses. So you see here we have sine of t there. You'll see it with or without, and it means the same exact thing. One thing that is important to note is that when you square the sine of an angle or the cosine of an angle, you don't write it like this. We usually put the square on the actual trig function before we tell what angle we're taking it up. So I have cosine squared t and sine squared t. That's how I write it when I square it. Okay, so if t is a real number, so remember t is standing for the measurement of that angle. If t is a real number and the point xy on the unit circle corresponds to that central angle t, then we have the cosine of t equals x, the sine of t equals y. This is just kind of summing up everything we just saw happen on those pictures of the unit circle a moment ago. Given a point P on the unit circle corresponding to an angle T, find the sine and the cosine. We do that by knowing that the sine of that angle corresponds to the y coordinate and the cosine corresponds to the x coordinate. So if I have this point here on my unit circle, and I'm told it's a unit circle, there's a 1 right there on the radius. I'm told that that point lives at negative square root 2 over 2, positive square root 2 over 2. So without knowing anything else about this circle and this angle, I know that the cosine of angle T is going to be equal to the x coordinate, which is negative square root 2 over 2. And I know that the sine of that angle T is going to be equal to the y coordinate, which is square root 2, positive square root 2 over 2. Y'all good so far? Pretty basic so far. I'll take everyone's silence as a yes. So stop me if it's a no. Okay, find the cosine of 90 degrees and the sine of 90 degrees. I have found that when you're first starting out learning all this stuff, it's easiest if you draw yourself a unit circle to think about. So here's my y-axis and my x-axis. Y'all don't laugh at my circles. It's hard enough to draw a circle as is, but drawing a circle on one of these bamboo tablets is extra special hard. Okay, so I have my initial sine here, and 90 degrees puts me right here on my unit circle. So because I know that this is a unit circle, that means that my radius is 1. So this has to be living at the point 0, 1. So pretty easy from there. The cosine of 90 degrees is equal to 0. The sine of 90 degrees is equal to 1. So like I said, to me it's easier to see it on the unit circle so that I can visualize, okay, what are those coordinates going to be? And now we're asked to find the sine and the cosine of an angle that is pi radians. So here's my circle. And remember, pi radians corresponds to a 180 degree angle. So there's my initial side. I'm going to go all the way 180 degrees. And since I know that this is the unit circle I'm dealing with, from the origin to the edge of the circle, that's got to be a measurement of 1, which means that I had to move 1 in the negative direction to get out there and up or down none off of the x-axis. So the cosine of pi is equal to -1. The sine of pi is equal to 0. Green check or red X? Okay, excellent. All 4 say yes, great. Okay, the Pythagorean identity, and this is where everything gets really real for us. So you should recall from your earlier studies of mathematics that the Pythagorean theorem is a relationship between the sides of a right triangle. So we have the legs of the right triangle as sides A and B, and your hypotenuse is C. And the Pythagorean theorem tells us that A squared plus B squared equals C squared. Well, if I have this right triangle inscribed in my unit circle here, I can come and relabel these sides. Remember, I have my X length, so that's like my A, and I have my Y leg of my right triangle, and that's going to be my B side. And then I have my hypotenuse, which is always 1 because it's a unit circle. So I can start replacing A, B, and C with X squared plus Y squared is equal to 1 squared, which is just 1. But I also just found out a moment ago that my X corresponds to the cosine of the central angle, and my Y value corresponds to the sine of the central angle. So I can completely transform the Pythagorean theorem to give me an identity that incorporates cosine and sine. So I have cosine squared of angle theta plus sine squared theta equals, well, 1 squared is just 1. So this is your Pythagorean identity. All right, so what are we going to do with this? Well, if you are given the sine of some angle T and its quadrant location, so remember the quadrant is going to change the sign, not sign as in trig function sign, but sign as in positive or negative. So remember, if you think back to your unit circle, if I have my point here, both my x and my y are positive. But if my point's in quadrant 2, my x value is going to be negative, my y value is going to be positive. Quadrant 3, my x and my y value are negative. And quadrant 4, my x is positive, my y is negative. So that's why you have to know the quadrant location so that you can figure out what sign, meaning positive or negative, do the values of the coordinates have here. So you're going to substitute your known values into the Pythagorean identity. If it's the sign, you know, you're going to be substituting in the sign and solving for the cosine. If it's the cosine, you know, you're going to substitute in for cosine, solve for sine. And then once you're done solving, then you go back and look and say, okay, it was in this quadrant, so it's got to be this particular sign, positive or negative. All right, so we are given here that the sine of t is equal to 3/7. So just up here, what I already know is that my y value is 3/7. And I'm also told that that central angle T lands in the second quadrant. So if this is my unit circle, then I am talking about landing over here. So before I even get going, because I've landed on the unit circle in the second quadrant, I know my x coordinate is going to be negative and my y coordinate is going to be positive, solely for the quadrant that it lives in. Okay, so we're going to use our Pythagorean identity to solve for the cosine. So we'll start with our Pythagorean identity, which is cosine squared of t plus sine squared of t equals 1. I don't know my cosine squared of t, but I know my sine of t is 3/7, so I'm going to add 3/7 and square it. And that is equal to 1. Cosine squared t equals, well, when I square a fraction, I square the numerator, square the denominator. So that's 9/49 equaling 1. Here I'm going to subtract 9/49 from both sides. And since I have 1 minus 9/49, I need to turn that 1 into 49ths as well. Well, 1 is the same thing as 49/49. So I've got 49/49 minus 9/49 on that right-hand side. So I end up with cosine squared of the central angle t is equal to, well, 49 minus 9 is 49. And now I need to take the square root of both sides to solve for the cosine because it's squared there. And that leaves me with the cosine of t equaling the square root of 40 over the square root of 49. The square root of 40 breaks down into 4 times 10. I can take the square root of 4 and get 2 square root 10, and the square root of 49 is 7. So what I just figured out is that the cosine of the central angle t is equal to 2 square root 10 over 7, as well as the x-coordinate. The x-coordinate is 2 square root 10 over 7. Okay, green check or red X on that. Okay, Jeremy's asking a question. I wonder if it has to do with the fractions or the reducing, or I'm sorry, simplifying the radical. I kind of got lost in 40 over 49. I figured it might have to do with the F word, fractions. Okay, let me give us a clean page. Actually, let me grab this so I can see where we are. And I'll work out all the fraction work. I was trying to squeeze it into that little area I left myself, so that's why I didn't show all my steps with the fractions. I knew better. Okay. So let me make sure that you're good up to this point, Jeremy. I have the cosine squared of t equaling 1 minus 9/49. Are you good? Are you good to that point, Jeremy? Okay. So when you add or subtract fractions, you have to have a common denominator. And right now, my 1 is over 1, or understood to be over 1, and my 9 is over a 49. So I need to get a 49 in my denominator. Well, you can't just go around and change a denominator because you feel like it, because that changes things, and it makes them different than what they are. But what is perfectly legal to do whenever you want is to multiply by 1. Multiplying by 1 does not change a thing. So what I do is I come in here and I multiply by a very clever form of 1, which is 49 over 49. That's just 1. 49 divided by 49 equals 1. So I'm not really changing that thing, I'm just making it look different. And we multiply fractions straight across. So now I have cosine squared t equals 49 49ths minus 9 49ths. Now I have a common denominator. It's perfectly legal for me to go ahead and subtract my numerators over my common denominator. So cosine squared t equals 40 over 49. I have no interest in what the cosine squared of t is. I want to know what the cosine of t is. So I need to take the square root of both sides. And when I do that, I get the square root of something squared on this left side, so it's just that thing. Cosine of t equals the square root of 40 divided by the square root of 49. This is the same thing as the square root of 4 times the square root of 10. And the square root of 49 is just 7. We know that. I can take the square root of 4 and get 2. So my final form of this cosine function is 2 square root 10 over 7. You good now, Jeremy? Okay, great. Matt's typing. Oh, you're welcome. Yeah, I always encourage y'all to ask the questions you have, because if you have them, 10 other people watching this video have that same question. So please ask whatever questions you have. Okay, so in this next one down at the, oh, I forgot to look at the second. Okay, actually, scratch everything that I just said with finishing off right here, because I forgot that we are living in the second quadrant. So that absolutely 100% makes our x value negative. The cosine of t is negative 2 square root 10 over 7. Okay, so you have to pay attention to the quadrant. All right, this next one, we're told that we live in quadrant 4. So we're dealing with a positive x value and a negative y value. So positive x, negative y for this point. And we're given the cosine in this one instead of the sine. So we have the cosine 24/25 squared plus the sine squared t equals 1. Okay, so 24 squared, if I'm not mistaken, is 576, but let me put it into my calculator to be on the safe side. Yes, so this is 576 over 625 plus sine squared t equals 1. Now I'm going to subtract 576 6/25 off of both sides. Okay, same deal here. I've got to get a common denominator. This is over 1, but I need 6/25 in the denominator, so I multiply by 1 in the form of 625 over 625. So that gives me 625 minus 576. Is everybody okay with me just stating that this time instead of actually writing it out there? Okay, I've got one green check. Is everybody following me? So, okay, I see you're typing, Jeremy. This is going to go away here. That's going to leave me with sine squared t equals 625 minus 576 is 49. You okay, Jeremy? Okay, great. And then that's over my common denominator, 625. Luckily, both of those are perfect squares, so when I come back and take the square root of both sides, I end up with the sine of t equaling either positive or negative 7/25. And I have to decide, okay, which one is it? Well, my y value, which is my sine of t, my y value is negative in the fourth quadrant, so I end up choosing negative 7/25. Okay. All right, so finding sine and cosine of our special angles. We have our 45, 45, 90 triangle and our 30, 60, 90 triangle that we need to look at. You should recall from way long ago mathematics studies that when you have a 45, 45, 90 triangle, I'm trying there. Okay. So this is 45 and 45. A 45, 45, 90 triangle, which for the record, 45 degrees is pi over 4 radians. When you have a 45, 45, 90 triangle, the legs of the right triangle are equal. So if this leg is X length, so is this leg. And when I'm inscribed in my unit circle, I know that my radius is 1. So that's why they have this right here. Because it's a 45, 45, 90 triangle, I know that X is equal to Y. So I can rewrite that point really as XX because they're the same thing. So we have that relationship, the Pythagorean theorem sets up, that says x squared plus y squared is equal to 1 in our unit circle. And because I can replace y with x, that's the same thing as saying x squared plus x squared is equal to 1. Well, when I combine 1x squared with 1x squared, I end up getting 2x squares equaling 1. And then I can divide 2 off of both sides. And that leaves me with x squared equaling 1/2. Take the square root of both sides. And x is equal to the square root of 1 over the square root of 2. The square root of 1 is just 1. Square root of 2 is square root of 2, but I can't leave it like that. I've got to rationalize the denominator. So I multiply again by a clever form of 1, square root 2 over square root 2. And 1 times the square root of 2 is just the square root of 2. The square root of 2 times the square root of 2 is the square root of 2 squared. And whenever you square something that is a square root, it goes away. And so this simplifies to the square root of 2 over 2. And it's the positive or the negative square root of 2 over 2, depending on what quadrant it lives in. Our pictures are showing it living in quadrant 1. So if we're just considering this particular triangle living here, then I know since my x and my y are the same, the coordinates of that point are square root 2 over 2, square root 2 over 2. Now if I had a 45-degree angle coming off into quadrant 2, I would know, okay, well that had to have a negative x value. The coordinates of that point would be negative square root 2 over 2 and square root 2 over 2. Is that good? Does that gel with y'all? Okay. Matt, how you doing, man? Okay. I see you're typing something. Surprisingly, I understood that. Awesome, Jeremy. And I'm going to wait to see which, good, struggling, more. Okay. All right, so we also have our 30, 60, 90 triangle, our other special right triangle that we need to look at. Okay, so we have a 30, 60, 90 triangle. Let's look at this center one here. If I were to place two 30, 60, 90 triangles together, I would end up getting a 60, 60, 60 triangle. That is an equilateral triangle. So if I'm looking at this as being the radius of my circle, then that would mean that this would also have to be the radius of my circle. So that's why they have R and R here. Well, what do you know about an equilateral triangle? I'll tell you what you know. Not only are all of the angles equal, they're all 60 degrees, but all of the sides are equal as well. So if I take this entire side into consideration, it also has to be equal to R. So if I just look at one of the triangles, then that side right there has to be equal to half of R. Let me stop there and say, did that make sense? how I'm able to call that leg, basically the y value, or the y side, the opposite side of the right triangle, half r. Good, good, good. Matt Bro's still looking for the green check. There it is. Okay, so the 30-degree angle is the same thing as pi over 6, by the way, pi over 6 radians. So for my 30-degree angle, or my pi over 6 radian angle, because I'm inscribed in the unit circle, my r is equal to 1. So if I pull that triangle out, so this is the 30-degree angle over here, this is the 60, and there's the 90. I know that this is 1, and this is 1/2 of 1, which is 1/2. Now I can use my Pythagorean theorem to solve for the x side of the triangle. So I have, which is the cosine of the 30-degree angle. So I have the cosine squared of pi over 6 plus sine squared of pi over 6. Well, I also already know that the sine of pi over 6 is 1/2. So I can input 1/2 squared has got to be equal to 1 squared. Okay, so cosine squared of pi over 6 plus, well, 1 squared is 1, 2 squared is 4, equals 1. Once again, back to my fractiony math, I need to subtract 1/4 off of both sides. So I need to create a denominator of 4 by multiplying by 1 in my clever form, 4 over 4. So I have the cosine squared of pi over 6 is equal to, well, 4 minus 1 is 3/4. I don't want to know what the cosine squared is. I want to know what the cosine is. So I need to take the square root of both sides. So I get the cosine of my 30-degree angle, or pi over 6 radian angle, is equal to the square root of 3 over the square root of 4, which is square root 3 over 2. Now I am able to say, in my 30, 60, 90 triangle, if I am looking for the sine and the cosine of the 30-degree angle, so this would be this point right here, I can now say that my cosine is square root 3 over 2, and my sine is 1/2. This is for the 30-degree angle. Okay, so now let's look at the 60-degree angle. Well, we can have the same picture here. Except it's the 60-degree angle I'm worried about this time. I still know that this is 1, and I still know that this is 1/2. But instead of that 1/2 representing sine, it now represents cosine, because this is how that angle would be situated in my unit circle. So I have the 60-degree here, the 30's up here now, and so that 1/2 side is now opposite the 60-degree angle. Okay, So I have the, oh goodness, I just got lost in what I was doing. No, I'm sorry, that is the wrong picture here. Let me start over with that. My apologies. It's the bottom side that's the 1/2. You can see where it splits, that equilateral triangle right here. So this is 1/2. This is 1. So my 1/2 is now my cosine. Sorry about that if I confused you. Okay, so, and this is my 60. Okay, so now I have the cosine squared, which is 1/2 squared, plus the sine squared of angle T, or theta, equals 1 squared. It's the same math that just happened over here. Look, I'm going to square that 1/2 and it's 1/4 plus sine squared T equals 1. Subtract 1/4 from both sides and I get sine squared equal to 3/4. Take the square root of both sides. This is positive or negative, by the way, depending on what quadrant you land in. All right, so I get the sine of T is equal to positive or negative square root 3 over 2. So this time when you've got the 30, 60, 90 triangle, let me get a different color here. This point right here, if I've got the 60-degree angle that I'm working with, that point has the coordinates 1/2 square root 3 over 2. So it's the exact flip-flop or inverse, if you will, of the sine and cosine of the 30-degree angle. Are there any questions about that? Yes, okay. Let me see what Jeremy has to ask. Why is the 1 squared? That's from the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. So that hypotenuse is the 1, so it gets squared too. But 1 squared is just 1, so. Oh, goodness. No worries on that. I'm the one that tried to play music for y'all and entertain y'all for 10 minutes and didn't even have my talk button on, so we'll chalk it up. Okay, so it is very beneficial to go through and label a full unit circle. So basically all this is going to do, there's really no work here except to summarize everything that we have just worked through. So we have, let's first go around, and this is just a picture of what we just did. You can see our coordinates that we figured out there. Let's go around our unit circle here, our blank unit circle, and just label the corresponding degrees. And then we'll go back around, and we actually did this in our last lesson. We'll go back and label all of the radian measurements for those same angle measures. So we start off, this is our 30-degree angle. Then we have our 45-degree angle, 60, 90, so 30, 60, 90, this is 120, and this is, let's see, 9 and 45, 135, yeah, because it's 15 degrees more. So this is 135. And then 15 degrees more, this is 150. And then 30 degrees more, this is 180. And 30 degrees more, this is 210. 15 degrees more, 225. 15 degrees more, 240. 30 degrees more, 270. 30 is 300. And I have 315, 330, and 360. Okay. Now, or 0. 0 or 360. But y'all know that. I'm not going to clog up my unit circle here with drawing the 0 on there. Okay, now let's go back and put the corresponding radian measurements. So let's hit all of our increments of 30, and then we'll come back and hit our increments of 45. Actually, no, let's get our 90s first. Those are easy. We have 180, which is pi. Half of that is pi over 2. Another half pi, that's 3 pi over 2. And then we get all the way around to 2 pi, or 0. Okay, our 30-degree angle corresponds to pi over 6. 45 degrees is pi over 4. 60 degrees is pi over 3. Okay, so I'm going to go from my 60-degree angle and go 60 more degrees to the 120. So that means I have 2 pi over 3. Because my first 60-degree angle was just pi over 3. So when I go another 60 degrees, that's 2 pi over 3. If I go another 60 degrees, that's 3 pi over 3, but that's 180, which I call pi. Another 60 degrees takes me to 240. So that's 4 pi over 3. Another 60 degrees takes me to 300. That's 5 pi over 3. And another 60 degrees takes me to 360. That's 6 pi over 3, which is the same thing as 2 pi. Okay. Let's see what we don't have in here. Okay, so start with a 30-degree angle. That's pi over 6. 30 more degrees, that's 60 degrees, which is 2 pi over 6, which is the same thing as pi over 3. Another 60 degrees is 3 pi over 6, so that's the same thing as pi over 2. Another 30 degrees is 4 pi over 6, which is the same thing as 2 pi over 3. Another 30 degrees is 5 pi over 6. Another 30 degrees is 6 pi over 6, which is 180, so we just call that pi. Another 30 is 7 pi over 6. Another 30 is 8 pi over 6, which is the same thing as 4 pi over 3. I'm at 240. Another 40 is 9 pi over 6. That's the same thing as 3 pi over 2 at 270. No, it's 9 pi over 6. I got to remember where I was. Another 30, 10 pi over 6. I'm at 300 degrees now. 10 pi over 6 is the same thing as 5 pi over 3. Another 30 is 11 pi over 6. And then another 30 takes me to 12 pi over 6, which is just 2 pi. Okay, so all we have are those 45-degree increments that we need to work in. So I have pi over 4. If I move another 45, that takes me to 90. That's 2 pi over 4, which is the same thing as pi over 2. Another 45 is 3 pi over 4. Then I have 4 pi over 4, which is at 180, so that's just pi. And this is 5 pi over 4. Another 45 is 6 pi over 4, which is the same thing as 3 pi over 2 at 270 degrees. And then I have 7 pi over 4 here. Okay, so I've labeled my entire triangle, my entire unit circle with its degree and its radian measures. Now I'm going to come back and write all of the coordinates for these points. So let's get the easy ones first. I have the point 1, 0 for a 0 degree angle or a 360 degree angle. Directly across the y-axis from that is my 180 degree angle. That is -1, 0. My 90 degree angle, I'm at 0, 1, and my 270 degree angle is 0, -1. Those are the easy ones. But we've already got all the other ones, so they'll be easy too. Okay, so pi over 6, we figured out a moment ago, is the square root of 3 over 2 and 1/2. My cosine and my sine. Let's go ahead and jump across the y-axis to our 5 pi over 6 angle, because we know it's going to have the same coordinates because it's got that same 30 degree angle right there, but it's going to have a negative x value or a negative cosine value. So this is simply negative square root 3 over 2, 1/2. Okay, I can move to my other 30 degree angle down in quadrant 3. Both my x and my y are negative. So negative square root 3 over 2, negative 1/2. And then I'll move to my quadrant 4 30 degree angle, and my x value is positive, but my y value is negative. Okay. My 90 triangle told me that the coordinates of that point on the unit circle are square root 2 over 2, square root 2 over 2. So now we just need to give positive and negative depending on what quadrant we live in. So this is negative square root 2 over 2, positive square root 2 over 2. Moving down to quadrant 3, this is negative square root 2 over 2, negative square root 2 over 2. And quadrant 4, this is positive square root 2 over 2 and negative square root 2 over 2. And finally, that 60 degree angle, remember it's the exact flip-flop of the 30 degree angle, so it's 1/2 square root 3 over 2. Here we have a negative x value, negative 1/2 square root 3 over 2. Going down to the third quadrant, negative 1/2, negative square root 3 over 2. And finally, the fourth quadrant, positive 1/2, negative square root 3 over 2. Done. You've got your entire unit circle there. You've got all the coordinates of the points on the unit circle that correspond to those very important angles or special angles. Is there anybody that has any questions about how we filled that circle out? Hopefully you would have asked them while we were going through it. Okay, Kim's got something. That was really, oh, very good. I'm glad that was helpful for you. Yeah, your book didn't have you go through the whole circle like this, so I actually went and found this blank unit circle just on Google Images because, yeah, I think it's very helpful to see it all in one place there. I'm glad you found that helpful as well, Ken. All right. So, how do we use our calculators to find sine and cosine? Well, you have a button on your calculator that says sine, and you have a button that says cosine. So it's just a matter of hitting that button and typing in the angle that you're wanting to take the sine or the cosine of and hitting enter. However, the important thing that you have to know is if your angle is given in radians, your calculator must be set in radian mode. If your angle is given in degrees, it's got to be set in degree mode. So that's what this top picture here is. When you click that mode button on your calculator, it's going to bring up this screen. If you arrow down a couple spaces, that'll bring you to the ability to toggle between radian or degree. So both of these problems at the bottom are given to us in radian. So everyone, check your calculator right now and make sure it says radian or that radian is highlighted. If it's not, move your cursor over radian so that you see it blinking and then hit enter, and it'll put it into radian mode. So make sure that your calculator is good to go. And as soon as it's good to go, I want for each of you to find the cosine of 5 pi over 3. You've got a pi key on your calculator. It's located as the second function on your caret key right there, off on the right-hand side. And when you get the answer of the cosine of 5 pi over 3, I want you to type your answer into the chat window. I'm doing it too. Okay. Okay. Ken got 0.5. Michelle got 0.5. Or 1/2. Yes, very good. Thank you, Ken. Jeremy's typing. Matt, are you giving it a go? Oh, you're not typing. Okay, it was showing you were. You must have been clicked into the chat window. Okay, so not sure if Matt's still with us or not, but yes, when you put it into your calculator, you hit the cosine button, it opens up a parenthesis. You literally type 5 pi divided by 3 in parentheses and hit enter. And the cosine of 5 pi over 3 is 0.5. It is also 1/2. 1/2 is 0.5. And if you look back, 5 pi over 3 is right, let me get a different color pen. 5 pi over 3 is right here. Cosine is the x value, 1/2. We just verified the work we did over there. Okay, try the sine of pi over 3. Sine of pi over 3, not going to be a very nice number. It's an irrational number. I get approximately, 0.8660. I'm rounding to the 4th decimal there. But I am willing to bet that if I put, let's see, the sine of pi over 3 is right here. if I put the square root of 3 divided by 2 in my calculator, I should get the same exact answer. And I do. Okay, Matt, I see you're typing there. Okay, while you're finishing typing, I'm going to go ahead and, are you talking? You cut out 15 seconds ago. Yeah, let me type back in case he can't hear me. Yes, I've been talking the whole time. Much to most of your dismay. Oh, it's working now. Okay, no worries, Matt. I'm glad you're back with us. And if you missed something, you know, I'll post this recording. You can certainly go back and look. Okay, real quick, let's talk about domain and range. So if you think about your unit circle, which is where your cosine and your sine functions are born out of, the domain of any function are all possible input values. So we're talking about our x values. And if you notice, the span that they can go through is only from -1 to +1. So my domain, or the boundaries of my x coordinates, is -1 to +1. Same thing with my y values. I can only live between -1 and +1. So the boundaries on my y coordinates is -1 to +1. So therefore, my domain is -1 to +1, and my range is -1 to +1 for both sine and cosine functions. The input into sine and cosine is the rotation from the positive x-axis. So let me repeat this. The input to the sine and the cosine functions is simply a rotation from the positive x-axis. You can move through the circle as many times as you want to. So that constitutes any real number. However, when you put it in there, you're only going to be able to get out that certain range of -1 to +1. And in reality, 4 pi, even though I've gone around the circle 2 times, is the equivalent of 2 pi, which is the equivalent of 0. And 0 lies between -1 and +1. So does this domain and range thing make sense with your sine and your cosine functions here? For now it does. Okay, I'm forewarned there, Jeremy. For now. It might not later, but for right now it does. Very good. Okay, last page, my friends. For any given angle in the first quadrant, there is an angle in the second quadrant with the same sine value. Makes sense. Because the sine value is the y-coordinate on the unit circle, the other angle with the same sine will share the same y value. That pretty much goes to say. But it's going to have the opposite x value. So if we take a look at this first circle here, I know that this point right here is going to have the exact same y value, but it's going to have the opposite x value. That's all that jumbo mumbo at the top is saying. Therefore, its cosine value will be the opposite of the first angle's cosine value. Likewise, there will be an angle in the fourth quadrant with the same cosine. So now we're looking at that second circle here, all this is saying is, well, obviously these live at the same x value. They have the same cosine, but they're going to have opposite sine values. The angle with the same cosine will share the same x value, but will have opposite y values. Therefore, we get these relationships set up. The sine of t, it is equal to the sine of alpha, and the cosine of t has got to be equal to the negative cosine of alpha. Sine of t equal to negative sine of beta, cosine t equal to the cosine of beta. And this one's alpha, and this one's beta here. So those are the relationships that are set up. Recall that an angle's reference angle is the acute angle T formed by the terminal side of the angle T and the horizontal axis. A reference angle is always an angle between 0 and 90 degrees, hence it being called acute, or 0 and pi radians. So they're just giving you different reference angles in different quadrants here. So, how to? If we're given an angle between 0 and 2 pi, and we want to find its reference angle, how do we do that? Well, for an angle in the first quadrant, it is its own reference angle. So that's pretty easy. Anything less than 90 degrees, that's your reference angle. For an angle in the second or third quadrant, the reference angle is pi minus the absolute value of pi minus t, or if it's given in degrees, the absolute value of 180 minus t. In the fourth quadrant, the reference angle is 2 pi minus t, or 360 minus t. If an angle is less than 0 or greater than 2 pi, add or subtract 2 pi as many times as you need to get it down between 0 and 2 pi. So, if I have a 225 degree angle, I'm talking about, let me draw my unit circle, my unit blob. 225 is about right here. Okay. And I want to find the reference angle. Well, the reference angle is this angle here. It's from the terminal side. Actually, I should be drawing it in there. From the terminal side back to the x-axis, and it's got to be acute. So, because this angle is in the third quadrant, the way I find that is to subtract it from 180 and take the absolute value. Since it's in degrees, I'm going to use 180. So the absolute value of 180 degrees minus 225 degrees is equal to the absolute value of 45 degrees. I'm sorry, negative 45 degrees. But the absolute value of that is just 45 degrees. So that's the measurement of the reference angle there. All right, and then finally we have a 5 pi over 3. Do we need to go back and look at our unit circle to remember where 5 pi over 3 is? I thought I had put the unit circle on this page. It must have disappeared. I must have not stuck it down to the page. We'll go back and look real quick. 5 pi over 3 lives right here. So it's that 300 degree angle. So it's in quadrant 4. And we're told when an angle, oh, that's where I put it. Oh, we're not on the last page yet? Did I lose a page? I did. I lost a page. Oh, there it is. Okay, I see. Sorry, got confused. Okay, so we have an angle in the fourth quadrant. So its reference angle is 2 pi minus 5 pi over 3. So Jeremy, here we go again. We've got our fractiony math that we have to work with. That's 2 pi over 1, but I need a 3 in the denominator, so I multiply by my clever form of 1, 3 over 3. So I have 6 pi over 3 minus 5 pi over 3, and that gives me a reference angle of pi over 3. All right, so I lied. I thought this was the last page. We still have another page to go. Using reference angles to find cosine and sine. So, how do we do this? We measure the angle between the terminal side of the given angle and the horizontal axis. That is the reference angle. We determine the values of the cosine and sine of the reference angle. Give the cosine as the same sign as the x value in the quadrant of the original angle, and give the sine as the same sign as the y value in the quadrant of the original angle. Okay, so a 315-degree angle. So down at the bottom right, I have my unit circle. Here's my 315-degree angle, which is 7 pi over 4. And that is living in quadrant 4. So remember, my point comes in the form of cosine theta, sine theta. Okay, so the cosine of 315 degrees is equal to the square root of 2 over 2. The sine of 315 degrees is equal to negative square root 2 over 2. And now I'm asked to find the sine and the cosine of the reference angle of negative pi over 6, right here. Okay, so negative pi over 6 actually puts me at 11 pi over 6, because I just dropped back pi over 6. Is everybody cool with that? How I was able to say that's the same thing as 11 pi over 6? Okay. Jeremy, Michelle, are y'all okay with that? Okay. You know, 2 pi is all the way around the circle, so that lands me back right here. And if I subtract pi over 6 from 2 pi, that's 12 pi over 6 minus pi over 6, which is 11 pi over 6. So it puts me right there as my reference angle. Did that help, Jeremy? Okay, great. Okay, so I know it's hard to see, but those coordinates are square root 3 over 2 and negative 1/2. So the cosine of negative pi over 6 is equal to square root 3 over 2, and the sine of negative pi over 6 is equal to negative 1/2. That's a negative 1/2. And then finally, find the coordinates of the point on the unit circle at an angle of 5 pi over 3. There's no work. You've already done all the work for it. It's right there. Those coordinates are 1/2 and negative square root 3 over 2. Sorry for going 17 minutes over. I thought I'd be able to do it, but I didn't.